Hi, so my name is Alex Bulazel, and I'm here to talk about detecting and evading automated malware analysis. So I'm a researcher on the CrowdStrike SRI team that Alexei leads. I'm also a consultant at Riverloop Security. 2015 graduate from RPI. This is based off some work that I worked on in college with Jeremy Blackthorne and Dr. Bulent-Jenner. So a little outline of this presentation. We're going to do an introduction to malware evasion, what that looks like, what you kind of see. How those fingerprints and way the evasion techniques are discovered, talk about antivirus emulators in general, then dive into a technique that I built at RPI to evade these antivirus systems and discover fingerprints in them. And then in closing, talk about some of the fundamental challenges of emulation and why you don't see emulators that aren't evadable and detectable. So, automated dynamic malware analysis. Static signature-based malware detection is pretty much useless in the face of 100 million plus new binaries in every year. You have 1+ million new binaries daily. Mostly these are just things being packed over and over again. It's not totally novel software. But it's very hard to say, oh, this byte sequence is associated with this particular malware when you have all these malware being pumped out with new keys and cryptography and new packers and things like that. So a big solution to that is automated dynamic analysis, where malware is run in what's called a sandbox. They actually run the malware in like a VM, observe what it does, and they can say, oh, this is malicious, or oh, it unpacked at runtime, it dropped the malware that we have a signature for. Oh, whoops. So a traditional malware sandbox, what you might be aware of, things like Cuckoo Sandbox, Anubis here, a number of commercial offerings, look kind of like this, where you have a stack of an operating system or a hypervisor like Xen, and then you have some instrumentation, maybe out-of-box, virtualized hardware, or that could be, again, Xen, QEMU, VMware Box, virtual machine, VMware, things like that, so like a virtual machine, basically. You're running a real copy of Windows, or maybe Linux, but for the most part, these are based on Windows. And then you're actually running the malware inside of there with in or out-of-box introspection or analysis of the malware, detecting what it's doing. And this is, generally we talk about malware sandboxing, you can get a thing like Cuckoo Sandbox, open source project, this is what it's going to look like. This is their general architecture. The problem is malware can detect that it's being run in one of these sandboxes, and it can try to evade that analysis. So it'll use a little trick like, maybe it knows there's a particular CPU bug in this emulator. It'll use that trick, detect that it's running, and then it'll exit. But if it detects that it's running on a real system, it'll go ahead and be malicious. And this is actually a real problem. According to some statistics from Last Line Labs, in the second half of 2015, over 80% of malware that they observed exhibited malicious behavior. So this is very rampant. Often packers will just include an anti-VM, anti-debug stub in the packer. So the malware author doesn't actually have to implement this themselves. They can just get a packer that does it for them. So we're going to talk about just a quick overview of the types of fingerprints that malware might use to detect and evade a sandbox. This is just kind of a refresher. You might be aware of some of these in general, but we're just going to go through some of them. So we came up with a classification about 7 classes of fingerprint, and we're going to walk through them. Environmental artifacts, these are probably the simplest class of fingerprints. These are things like a unique username, or a unique registry entry, a unique computer name that's associated with a particular analysis system. Or you could look for things like a particular driver. If you see like cuckoosandbox.sys, you might know you're running inside Cuckoo Sandbox. You could also have heuristic ones. For example, if you know that you're probably going to run in a VM, you look for artifacts associated with that particular VM. Like if you see vmmon.sys, you know you're probably in VMware. And you also have heuristics like if you see a single CPU system in today, most people don't run single CPU systems on their personal computers. A lightweight malware sandbox might be configured to be a single CPU system. Or you have this quote from Garfinkel where they talk about, VMware emulates this particular chipset, which is way, way outdated. So if you ever see that, it just seems discongruous. Real software, real hardware isn't configured like this. Timing bugs. So these are discrepancies in virtualization and timing. It's probably one of the hardest things to get right about virtualization and emulation. Most applications don't demand exactly, tick-accurate emulation. In some cases, like for example, video game emulation sometimes demands that, but most consumer software, if you want to run Microsoft Word or some web app in a VM, it doesn't need to be exactly correct in terms of timing. So VMs always have problems emulating timing and getting exactly right, but malware can exploit that to detect that it's running inside a VM. CPU red pills. When you have an instruction set as complex as x86, where you have over 1,500 instructions, which are poorly documented, you're going to have incongruities when you emulate the instruction set, some weird edge cases. This is actually so bad. A good friend of mine, Rolf Rolls, who's done a lot of work on this topic and a lot of reversing, he talks about if you open the x86 manual, on the first instruction you look at, I believe it's AAA, that instruction has undefined behavior in the manual, and you have to actually go run it on a CPU and observe what actually it does. It sets what is this status flag? How's it set? Because it's undefined officially according to spec, and that's the first instruction, an instruction that's in the base instruction set. Let alone all these bizarre floating point instructions, cryptographic instructions, things like that. Very hard to get these right in an emulator. Process introspection. These are artifacts inside a running process, a malware process running in a sandbox that it might use to detect it's running there. So for example, if you inject a DLL into a piece of malware that's under analysis, it could look for that DLL being loaded and then know that it's being analyzed. And we also have some more subtle ones, like if page permissions are tweaked in a strange way that your analysis system uses. For example, you might want to set a page to be only read-write. When you try to execute on that, they can trap and they can know you've hit that page. Different things like that analysis systems do for various reasons. So you can look for these and discover that you're being analyzed. Reverse Turing tests. These are a really interesting type of artifact. This is when malware tests the computer to see is a human actually sitting there. Normally the Turing test is a human trying to test a computer. Is this a human or not? This is the other way around. The computer wants to know, are you a real human? So it might look for things like mouse or keyboard input. And this could be very simple, like, has there been a key press at all? To very complex, like, are you moving the mouse with no acceleration, an exact straight line from point to point? Are you clicking keyboards every half a second you have a key press, or is there some natural rhythm, some natural pattern that a real human would have? And you also have what we call wear and tear artifacts. There's actually a paper coming out at IEEE S&P this summer that actually cited my research on this topic, where they looked at wear and tear artifacts, things like login times. They used certificate revocation lists, where if you're on a real computer browsing the internet, sometimes internet certs will be revoked here and there, and that's kind of an artifact of just using a computer for real, browsing the internet. This will happen. If you have a clean sandbox system where you set it up once and just start running malware in there with a snapshot and then revert to the snapshot when you're done, you're not going to have that wear and tear. On a mobile analysis system, you'd expect to see people taking photos, on a cell phone. They're going to take photos of things. If there's no photos on someone's cell phone, that's kind of suspicious. So there's all these kind of just things that crop up naturally from people using systems. It's just there, and you can look for those. And I think this is actually going to be a very interesting area of research going forward as emulation gets more and more accurate. And as people can mitigate, to some extent, CPU red pills and timing bugs, it's going to be very hard to make a system that looks like a real person has really used it. Network artifacts. When you have these malware analysis systems, you may connect them to the internet. And a lot of malware only runs when it can grab the next stage from a server or take some C2 commands, something like that. So you can look for things like if they emulate network connectivity, if they don't actually provide you with real network connectivity, you could probably detect that. Or you could detect things like extremely fast internet speed. So if I'm running my sandbox in like an Amazon AWS instance, you're going to have really, really fast internet, faster than a normal consumer would have. So you can do tests and see, like, is my internet incredibly fast? Because only like an industrial company that's doing mass scale malware analysis would really have that industrial speed internet connection. So that's just kind of a review of different ways that malware might detect analysis, just a refresher. So how are these fingerprints of analysis actually discovered? So generally what you can do is you can look at the underlying open source or freely available technologies that's in this kind of stack of a malware analysis sandbox. So you see at every level these are mostly open source tools or things you can just download for free, test them out, things like Qemu. VMware is not open source, but you can download a copy and you can play with it. And you can just easily observe things about the analysis environment. So here, for example, is a VM I have. I downloaded a tool called Paranoid Fish, PA-Fish. It's on GitHub. And it will just look for different heuristic fingerprints of virtual machines when you run it. So I just ran PA-Fish, and it spits out a whole bunch of fingerprints that it observed inside VMware. And because it's VMware, it's just a VM that I'm running. I can just print the standard out, look at a terminal, and see all these artifacts. It's really easy to find them. There's also dynamic fingerprint discovery. So for example, if your sandbox is not built on technologies that are freely available or don't know what they are, what I might do is I might write a piece of malware, upload it to VirusTotal, and then if you're a big antivirus company, you're going to be scraping VirusTotal, pulling down all the new malware, and running it through your sandbox system. And let's say these are 3 fingerprints of your sandbox system, sandbox user, debug process, analysis driver. When I'm running in your system, I can look for them, and I can send them out to a C2 server that I control, and I could just post a message to my C2 server, or do a GET request here and say, the username inside the system is sandbox, and this is the IP address, and this is the MAC address, all these kind of information that fingerprints the system. And then I can write malware in the future that looks for those particular artifacts and chooses not to run if it observes them. So you don't actually have to have access to the analysis stack that a particular antivirus company is using to discover these artifacts. Another trick you can use in the case that they do allow you to upload directly to their sandbox and they give you a rich analysis report. For example, they give you a report that says, created this file, created this process, access this web URL. You can use that as a side channel. So if they tell you whatever file the malware created, you can create a file named sandboxuser.txt, and it will come back with a report and says, created these files, and you've now kind of profiled the system by exploiting that as a bit of a side channel. So this is an attack that's been used against the Anubis system, which is a very early academic system in this field, very notable, and was the basis and inspiration for a lot of systems going forward. People started doing this to Anubis. So that's how you would discover these fingerprints in a high-end system like this. But how about consumer antivirus products, which are ultimately protecting millions or hundreds of millions, if not billions of computers worldwide? There's this common narrative in the public, you look on Twitter, things like that. People always talk about how antivirus is so bad, antivirus makes you vulnerable. But very few people have actually done research in antivirus internals, talked about vulnerabilities in antivirus. So we wanted to look at that, and particularly at the emulators that they use. So again, they're interesting because they're protecting real computers. This isn't a system that's just used for a particular enterprise or by a particular malware analyst. These are protecting end users worldwide and really the front lines of defense against malware. But unlike the high-end academic and industrial systems like Cuckoo and Anubis, things like that, or a number of endpoint protection products, there's no easy way to identify fingerprints for analysis from consumer AVs. And there's 2 approaches that have been proposed before, reverse engineering, which is probably too hard, and side channel attacks, which we think are too slow. We're going to review both of those. So AV emulators are very limited because they have to run on consumer endpoint systems, run quickly, and there's generally really poor software engineering in the AV industry. So again, this is a traditional malware sandbox. Just showed you this the other slide. This is what it looks like. Again, a number of layers of tools and technologies that are freely available, widely available. Now compare this to an antivirus emulator. These are generally built in-house by an AV company, and the whole stack is going to be built internally. They don't want to release their code because of, say, GPL restrictions that Chemo might have. They want it to be fast and efficient. They want to have their own custom tooling and want to integrate it with their signature system. So in the previous example, again, we're building on a stack of open source tools and probably running a real copy of Windows inside a VM and running the malware inside of there. Now in a consumer AV, you're going to have an x86 emulator or whatever CPU architecture you're working on. Generally, it's going to be x86. And they're going to have a homegrown, in-house built x86 emulator. Alongside that, they're going to have a user mode Windows API emulator to emulate common Windows API calls or whatever operating system you're emulating, but generally it's going to be Windows. To emulate those calls, so they don't actually have a real kernel underlying this. They're not running a real copy of Windows. They're running this one malware process, and when they see it make a library call, they're going to emulate that call. And they might have heuristics like if you call, exec process, that's really suspicious, and they might flag you as malware if you do that. And those are going to have an environment built alongside the emulator. So when you do a call like, what processes are running on the system or enumerate files on someone's desktop, they're going to have a fake file system, a fake process listing, so forth. So again, this whole area in the red box is all pretty opaque to you as the end user. This is all like homegrown stuff in the AV company, probably obfuscated, probably encrypted, maybe in a non-standard custom binary format. It's all pretty much a black box and very hard to get at and hard to observe. And the only output you really get is an analysis report of what pieces of malware were detected when the malware binary was run. So the kind of obvious approach one would take to this is they just go in and dive in and start reversing the antivirus emulator. But this is actually really, really challenging, very time-consuming. It requires extensive expert knowledge of all these different domains. So when you're looking at an emulator for x86 CPUs and for the Windows API, you're probably going to need to know a lot about x86. If you want to identify functions that emulate a move instruction, you should probably know what a move instruction is in the first place. And you're just going to have a ton of knowledge about x86, about Windows internals in order to understand all the library calls that are going on, that they're emulating certain library calls, what those look like, what a DLL looks like, how to parse things. Malware behavior, because they're designed to analyze malware. And also, you're probably going to need to know a lot about anti-analysis and how to bypass all these techniques that the AV industry observes in malware, and then they pull those techniques into their AV products to make them hard to analyze. So you're going to have to circumvent all these anti-debug things they do, maybe attach from the kernel. It's just a real pain to do. It is technically possible. Rolf Rolls, one of the probably best reverse engineers in the world, really smart guy. He's done this a lot. This is a question we posted on Reverse Engineering Stack Exchange, and he was like, oh yeah, I've done this many times before. But not everyone is Rolf Rolls, not everyone has as much time to work on this topic. That said, it is technically possible. Again, this is some work I've been doing recently, looking at a particular antivirus product. And here's their adv-api32.dll. This is not the real one. This is the emulators, adv-api32. I had to pull this out from the running process, from the kernel. It's not even a standard like PE or ELF file format. It's a custom binary format. I was using this tool called Binary Ninja you might have heard about, and it has really good support for scripting. And I was able to write my own custom loader for this custom binary format, load this in, and then you could actually discover weird artifacts like here, reg close key. There's a compare. ESI to ERIF, that's a little endian, that's fire. So evidently, this is some particular artifact of this AV that in some cases, I guess they'll return fire as a registry H key, a key. And I guess if you opened a registry entry and you saw your H key was fire, you might know you're running in this particular emulator. Just a weird thing they have in there. I don't know why. I haven't dug any further, but you can see evidence of strange things like that. Here's another one in their emulation of get username A or get username W. It's actually a common function to handle both of those. Here you'll see this string user. So if you do a call to get username, they'll return user. Again, that's a very common name. That's probably not a great artifact to identify this AV. But you can dig these fingerprints and artifacts out. And again, these are very simple environmental ones. These are very simple strings. It would be much harder to find like an inconsistency in x86 emulation by just looking at their emulation of that code in a disassembler. So again, the only output is an analysis report. All you get to know is what malware was seen when they run your malware. So how can you exploit that as a side channel to extract information? So prior researchers before us approached it like this. They began with a question, a true or false question. Is function X emulated correctly, for example? And then they wrote some binary that looked like this. If function X does not return the correct value that they expect, they're going to drop malware. Otherwise, they're just going to exit. They then compile this code, pass it to the AV, have it run in their antivirus emulator, the AV emulator, and while it's run, it does a call to function X, which is probably, it's going to be emulated by the AV emulator and might not have the correct semantics of that function call in a real Windows system. So it'll come back, and if function X does not return the correct value, it'll drop malware. The AV will detect malware and come back, and they will then know that function X was not emulated correctly. Or they'll exit if function X was emulated correctly. No malware will be detected, and they'll know that. So you kind of get this one-bit side channel. You get to ask a true or false query to the AV with each run of a piece of malware you put through it. But that's very slow, very time-staking, and it's not good for finding these more subtle artifacts we want to find that are going to require lots of messing around, lots of dumping out data. So we wanted a faster approach than that. So what we did is we built a tool called AV Leak. So we're going to talk about that now. A way you can think about it, my friend Ryan has said to me, you might think of this as standard out for antivirus. we showed the PA fish example earlier, where if you're running in VMware, you can just print to the terminal and you can observe that on the screen. But there's no such similar thing for a consumer AV, particularly one that I don't have the debug build, I don't have all the instrumentation that the AV company might have. So we built a side channel to enable us to print and extract information as easily as printing to standard out. So our technique was we mapped specific values of specific viruses and pieces of malware to specific byte values. So for example here, A to Morris, B to Code Red, C to Zeus, and so forth. And we have this big table correlating a particular malware name or particular malware binary to a given letter. And then what we do is we create that array, mapping all these pieces of malware to particular letters. And we just have this big bundle of all these malware binaries, all encrypted so they can't be detected with a static signature, all in a big table. And we have a call like get username. We want to learn what is the username inside this emulator. So rather than doing the prior approach, whereas this slow and steady one-bit testing, is the letter A, is the letter B, is the letter C, is it D, and so forth. What we do is we compile this binary with this big table of all the letters in the alphabet and other byte values. We put it inside the antivirus. We tell it to go scan our binary. And now, for each byte returned by the call to get username, we're going to drop the piece of malware that corresponds to that letter. So what that's going to look like, here we have the username being EMU. We're going to drop the piece of malware that stands for E in our array, then the one for M in our array, and the one for U in our array. This is, again, inside the emulator, so we're not really dropping this to real disk. We're calling create file inside the emulator. The emulator is capturing that call to create file and taking whatever buffer we do write file. We give it this buffer of data to write out. It's going to then scan that buffer, see a piece of malware it recognizes, and go, oh, I know this piece of malware. This is just a dropper for Morris or Code Red or Zeus or whatever. So it comes back with our analysis report and says, oh, we found Sasser, Bagel, and Blaster. And we can go across our table and correlate those back and say, oh, well, if you saw Sasser, you saw E, then you saw M, then you saw U. We know now that the username inside this emulator is EMU. So we very quickly extract that information. And this is a very simple example. We can do all kinds of things beyond something so simple as this. So now we have that fingerprint EMU that uniquely identifies this particular AV emulator. We can go now write malware that looks for username EMU and then chooses not to run if it sees it. So in testing, we tested 4 commercial antivirus products: Kaspersky, AVG, Bitdefender, and VBA. Chose these from a variety of levels of quality. Obviously, Kaspersky has a very good reputation as catching a lot of malware. We wanted to see if that was true. VBA, not as much a reputation. Bitdefender is licensed out to 20+ other AV products and also a number of endpoint protection products. So a lot of market coverage there. And we tested all 4 of these. And now we're going to go into a demo. Before I go to the demo, I want to ask, does anyone not understand that idea of leaking information out bit by bit? Anyone have any questions? Please feel free to speak up if that doesn't make sense to you. Yeah. So actually, yes, if you have a repeated letter, it depends on the AV's behavior. For example, Kaspersky will only detect a given piece of malware once. So if I want to print, A, and I had a particular piece of malware that mapped to A, if I drop that malware like 30 times to represent 30 A's, it would only detect in the first run. So in those cases, we basically have a unique table of malware for each byte position. This is really getting into the internals of the system, but the Kaspersky, we actually compile over 8,000 pieces of malware into the binaries that we give to the Kaspersky emulator so that we can leak information from them effectively and efficiently. Any other questions? Anyone else understand this or have any questions about it? All right, then I'm going to dive right into a demo. We're going to show this live. So we're now applying that technique I just showed you to leak out information in real time live on this system from these different emulators. So right here, we're leaking at argv0. What is the name of my program running inside the emulator? And here in Kaspersky, you can see it's randomized each time. And I believe that their algorithm is between 7 to 13 letters at a time. It'll just give you random names. So you can't fingerprint that particular artifact. It's such a common thing that malware does that they knew to try to prevent that by just randomizing the name with each run. In Bitdefender, your name is ctestapp.exe. And this is actually still in there. I've presented this work before. They never fixed it. This has been used in APTs that I'm going to show later in the presentation. They never fixed it. This has been at least since 2011. It's been there because there was an APT in 2011 using that artifact. So you can just look, is my name test app? If it is, you know you're running in Bitdefender, and it can evade 20 plus consumer antivirus products and various endpoint protection products that might use Bitdefender. So it's super easy. AVG calls you quite a long path. We skipped dumping the whole path in the interest of time, but they then call you MWSMPL, presumably malware sample, and VBA your self.exe. Now we're going to dump some of the first 10 processes that are running in Bitdefender. This is according to a call to get proc info or whatever the API is that will show you information about running processes. We're enumerating what processes are quote unquote running. Again, they're only really analyzing your particular piece of malware in there, but they want to have a fake environment that looks real, looks believable. I also wanted to show you, again, this is running real in real time. And we built a whole scripting interface around the AV leak tool and this technique. So this is the actual code that's running right now. So you can see we're just directing it to different files we want to run. And we can just tell it, oh, go dump this information from Kaspersky, go dump it from Bitdefender, so forth. It's super easy to script out these interactions. So again, you'll see right here in Bitdefender, yourself, you have PID 8, so you're running before like essential system services. You're running really early. Real malware wouldn't be running that early. And also, you notice that there are 6 different processes with the PID number 12. Obviously, a PID is unique, so this is just strange. I mean, some programmer hard-coded this array and said, oh, PID 12, PID 12, PID 12, maybe there's copying and pasting or something. But that's totally unbelievable. 1, that you would have PID 8, and 2, that 6 different processes would have the same PID. That's totally impossible in real life. Here we're looking at OS API inconsistencies. So here in AVG, when you can use the format message with a DW message ID from get last error, it will format a message out for you and tell you what an error code means. So error code 0, probably the most common error code you're going to see, just means success. It should return the operation completed successfully. It returns mid 000, just the hexadecimal value of the message ID you pass in. And if we say set it to dead beef, it'll say mid dead beef. So here they have an emulation for format message, which is just totally wrong and easily fingerprintable. Some more subtle checks, looking at Windows heap allocations. So normally if you do a heap allocation of size 0, like a malloc 0, you will get a 16-byte chunk of memory on the heap. And you could do this over and over again. So here you'll see D0, E0, F0. These are obviously in hexadecimal. That's hex 10. That's like 16-byte differences because each call to heap allocate 0 gives you a 16-byte chunk, and they give you the next chunk, and so forth. But in VBA, they give you 1-page large allocations, 4,000, 5,000, 6,000. And here in Bitdefender, they give you 8-byte large allocations. Again, in a real system, it would always be rounded up to 16 bytes. Now we're going to look at some process introspection. So we did a call to load library, get proc address in kernel 32. And we just dumped what was returned by a call to sleep, or asking for the process address of sleep. And it gives us this code in hex. Again, because we have a whole scriptable API around this tool, we were able to integrate the Capstone engine, which is a really awesome disassembly engine. And we should just disassemble that code on demand right now, live. And you'll see it disassembles to this. This really nonsensical code does not make sense. You would not see this in a real call to sleep. You would see a call to sleep X. Sleep X would then do an interrupt, and you trap into the kernel. Your process would be put to sleep. You wouldn't have this bizarre jumble of incoherent instructions. We're going to talk actually a little bit later about what these instructions mean. Here, we're looking at loaded modules in memory as accessed via the PEB, the process environment block. This is a common in-memory data structure in all Windows processes. And here in a real system, you can see the loaded DLLs in my process, their base address, their entry point, and their size of image. In Bitdefender here, we're going to see NTDLL. It's at a believable base address. We're going to see its entry point. Again, on the real system, NTDLL does not have an entry point. It's just loaded there. In Bitdefender, it does have an entry point, so that's an inconsistency, and a very subtle one. If you saw malware that was checking, load library NTDLL, then parsing the PE headers to look for a, address of entry point, and it found that it had one, and then if it saw that, it would decide not to run. That's such a bizarre, subtle thing. Excuse me. That it would be very hard to tell what it's trying to evade, or even in the first place, kind of detect that that was an evasion feature. You might just think that it was, say, trying to look for a particular address of an undocumented syscall. You really have to know all about these Windows internals, know that the real NTDLL does not have an entry point, in order to know that that's actually a particular fingerprint in a particular antivirus software. You'll also see their NTDLL has a very small size of image. It's like less than a 16th the size of the real NTDLL, probably less than a 20th the size, actually. Real small, again, very subtle artifact. Here, their kernel 32 actually seems believable. And again, this is all in real time. Again, this is not a canned demo. This is in real time. We're compiling viruses, compiling all this malware, telling Bitdefender, please scan this, getting the output from Bitdefender, and then translating it back to these byte values and printing them out on stage live right now. Now here you'll see that the third module in Bitdefender is called null. There's no such DLL. You'll also see its base address is CD, 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 CD. That's kernel memory. Anything above hex 8 and then 7 zeros is going to be on the kernel user divide. So this is a kernel address. If you do reference this, you will immediately segfault. I've actually tried in Bitdefender seeing is there something actually mapped to virtual address CD, 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 CD. There's not. It's just some bizarre artifact there. Also, its size of images, CD, 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 CD. So this is just very strange. You could look for this in Bitdefender, look for that address. And also they repeat NTDL another time for some reason. Now looking at timing artifacts. On a real system, when you call sleep, again, you're going to have to trap into the kernel. The kernel is then going to put your process to sleep, wake it up sometime later. It's probably going to set an alert, get a callback when that timer is over. Some of these timers have resolutions of only, say, 10 milliseconds at a time. So I'll notice on my VM here, a call to sleep for 1 millisecond actually incurs a time difference of about 15 milliseconds. It actually takes that long. Your process actually to be put to sleep and woken back up again, even though you only asked to sleep for 1 millisecond. But in AVG, you'll see here, we go to sleep at 41 and then 16 milliseconds. We wake up immediately 1 millisecond later. So there's no accounting for the overhead that the sleep call actually takes. In Kaspersky, they do the same thing. We do a call to sleep for 1 minute, 10 calls, and we'll notice that here we went from 5165 to 5765. It's exactly 10 minutes later. Again, on a real system, there'd be overhead and just churn and things like that. Other processes are going to get scheduled. This is not believable. And my favorite is in Bitdefender, where you're going to see this. They actually, when you call sleep for 1 millisecond, I think they add 15,000 milliseconds to your time. So 10 calls to sleep, that's 10 minutes of sleep, is enough to cause an integer overflow for the integer that they have there. And you'll see it goes, after 10 minutes, it actually rolls over to a smaller value. Network emulation. In Kaspersky, they actually emulate network connectivity. So when you make any network request, it always succeeds. And they always give you a valid PE binary back. And it has the MZ header. We skip forward in the interest of time. They cannot be run in DOS mode, but there's no space between in and DOS. And then they also put this bracket, downloaded bracket thing, and then the address of the URL you download it from. So we did a call to URL, download to file, with google.com. In Kaspersky, their emulator comes back and just returns this file from our call. One of my other favorite artifacts, CPU behavior. We can look at fold pi, such a strange, complex instruction set instruction. In x86, there's actually an instruction that will push the value pi onto the FPU stack. I think it's slightly truncated here. I don't know if this is a full floating point value, but you see 3.14159. This is an actual instruction, puts this on the floating point stack, and we just pulled it off from the floating point stack with some inline assembly. In Kaspersky, they get it right, and they actually emulate 3.14159.3. In VBA, the fold pi instruction returns 0. And Bitdefender just chokes when you run this instruction. It just exits. So you could just put fold pi at the beginning of your malware. If you're in Bitdefender, it'll exit, and they won't scan you. They won't detect anything. Now, running a NOP on a real system, a NOP is a no-op, no registered states changed other than EIP. So everything stays the same. You'll see it's all the same here after we run a NOP. But in Kaspersky, you'll notice that the ESI register changes during the course of a NOP for no reason at all. So you could just run a NOP and say, is ESI the same before and after this NOP? And NOP literally means no operation. But they do some operation for some reason. This is just a bug in Kaspersky. Now, another one in the x86 standard call convention, the EAX register has the return value from a call. EBX is not volatile. It has to stay the same before and after a function call. And ECX and EDX are allowed to be smashed, so generally they are. In a real system, If we set EBX, ECX, and EDX to BBB, CCC, and DDD, you'll notice EBX is left BBB after the call, EDX and ECX are smashed. But in Kaspersky, here in the interest of time, we just show the registers after the call. EBX, ECX, and EDX all maintain their value. You would also notice that normally when you do a function call, the function will run and have some artifacts on the stack. You can look kind of on the stack above you in unmapped stack space. This is undefined behavior, but you can do it. And you could see, was there evidence of local variables and operations on the stack before you read it to my stack frame? In these emulators, because they just trap right to an emulator and emulate your code, you're not going to see that. And in this course of this demo, we compiled 279 binaries and leaked 572 bytes. So that's quite a lot of information actually for only 500 bytes. And again, that was in real time, almost 280 pieces of malware compiled, scanned, and then correlated back through our system in real time there on stage. So going back to the presentation, some other results I wanted to talk about besides the one I just showed in the demo. Again, we talked about some of the hard-coded environmental values. Get computer name returns these unique values in these different AVs. The ElixCZ one is particularly interesting. If you look that up, there's a guy who was like a cracking website, like cracking video games and stuff back from like the 90s. Maybe that guy went and worked in an AV company and put his name in the emulator. I don't know, but it is a unique handle from a guy who'd like done work before and breaking antivirus. File system registry. We're going to have another demo at the end while I take questions, but it's really interesting to dump out file systems. And you'll find these unique things like in Bitdefender, these kind of Easter eggs, like these files with names like Batman's Spike. And it's actually written in Romanian. And I had a native Romanian speaker translate that, the Tzipa a la Batman. And he actually told me that Romanian keyboards are laid out such that I think one of these particular words is misspelled. And it's misspelled in a way that is very common for people typing on Romanian keyboards. And Bitdefender is based in Romania. So it's kind of this archaeology of picking apart these little nuances and things that are left in there by programmers. In Kaspersky, you have a bunch of files with like random file names. But if you look at the files, you can tell someone kind of smashed their hands randomly on a QWERTY keyboard, like KOIO. Those are 3 adjacent letters. So you can tell someone's just smashing their hands on a QWERTY keyboard and whatever came up, they put it in the emulator as a fake file. Other AV products, a lot of these AV tools, in their emulators, they emulate the presence of other AV products to see if maybe malware wants to say particularly like a particular directory for a particular AV product. If they see that, that might be a heuristic that malware is AV evasive. Network emulation, I already showed you that. Hard-coded start times, kind of at the intersection of the timing artifacts and the environmental artifacts. You have hard-coded start times. So, for example, in Kaspersky, it's always 11 a.m. on July 13th, 2012. So you can even write malware that says if the date is not 2017 or after, don't run. But they all have these hard-coded times, and you also have inconsistency between even different various ways of getting time. So a call to get system times file time and VBA will return just all null bytes, but a call to get system time will return November 3rd, 2014. Or Bitdefender just crashes when you call NT-query system time. They just can't emulate it. So those are kind of funny. Process introspection, again, showed you some of that. The heap metadata, the periodicity of allocations of the heap, bizarre structures on the PEB, data left on the stack of function calls, DLLs in memory. Fake library code, we showed a bit of that with VBA, dumping code at a call to get proc address, what actually is there. And again, I said we were going to talk about what those nonsensical, bizarre instructions mean. What these actually are is, this is such a strange instruction in AVG. Lock, move, EBX, and hex FF, 1 byte that is unique per library. So kernel 32 all has 1 byte there, and ADV API has a different byte there. All these libraries have unique bytes, and then 2 bytes representing a function number. So what these actually are is when this passes through the CPU emulator that's built at the AV company, their emulation for lock, move, EBX presumably then looks for, is the high byte FF? And if it is, I'm going to look at the other 3 bytes, and then know what function to emulate by looking at them. So each function has a unique identifier there. And when those pass through the CPU emulator, it knows kind of to escape, to go emulate this particular call and then come back to the malware. And I was actually experimenting with this and seeing if I could remap functions and things like that. They're actually pretty good at making sure these only trigger if you run them from actual set addresses. So you can't just run lockmovie, bx, ff, whatever in your malware in your .text section. You have to actually go to a particular address and it says, if at this address I saw this value, emulate this function call. Again, CPU red pills showed you this, dumping out CPU values. And some discussion to conclude. So common themes, these simple evasion techniques are really sufficient for evasion. I've used all these. I've written like simple like eCar malware droppers. It's just a sample file. It's not malicious, but it's a standard industry test file in the AV industry. I'll upload those to VirusTotal or drop some DOS malware from the 1980s and see if I get detected, and I'll use these artifacts. And I'll get detected by everyone but the one particular AV that I put an artifact in for. It said, if I'm running Bitdefender, don't run. And you can tell who's using Bitdefender, who's not, by doing stuff like that. And also very little heuristic classification of malware based on these evasive behaviors. You would think that certain calls, certain instructions, certain memory accesses would be a heuristic. Like, why are you crawling the PEB and looking for the flag that represents if the debugger is present? But other than Kaspersky doing a little bit of it when I was doing in-memory DLL scanning and actually pulling out DLLs from memory, most AVs don't have a heuristic, just the memory accesses, the library calls, the instructions you're running, that they themselves are suspicious and kind of associated with evasion. Malware authors in the wild are already using these. This is before I ever presented this publicly. I would just search these strings and find malware reports online with malware that was using particular artifacts like the KL auto-generated, that's a string from Kaspersky, or the Fantoma Deficer, that's a string from Bitdefender. Malware authors already know about some of these artifacts and are using them in the wild. And it's not only generic crimeware and boring malware, it's advanced APTs as well. This is the Evil Bunny malware from the so-called Animal Farm APT, which was evading Bitdefender back in 2011. It would check, is my name test app, and if it was, it wouldn't run. And this other name, the AFYJ thing, that looks kind of one of those randomized names from Kaspersky. I don't know what it is, but we certainly know that test app is a Bitdefender artifact. So advanced APT malware from the Animal Farm APT was evading Bitdefender back 6 years ago in 2011, and those artifacts are still there. I discovered them independently. Marion Marshalik, who discovered this malware, was kind enough to share a sample. I got to reverse it. So it's really cool to see, kind of motivating to see that people in the wild are using this stuff too. Again, 100% evasion rate when we were testing. If I uploaded something to VirusTotal, I would very easy to evade stuff. And I think in terms of future work, where do you want to take this? It's interesting to evade antivirus software. It's a cool problem. But the next step is exploiting emulators. So the thing is, there's a lot of talk in the public about, AV makes you unsafe. Tavis Ormandy has demonstrated a lot of AV vulnerabilities. But actually weaponizing some of those vulnerabilities that Tavis made would be pretty hard. It would be difficult to use them in an operational context or to write a worm that uses them or anything like that. They're cool bugs, but are they really being exploited in the wild? Are they really exploitable in some cases? If you have like a parsing bug in, say, a PE parser, it might be hard to exploit that in the face of modern mitigations like DEP and ASLR. Back in the 80s or 90s when you just had a straight stack smash, maybe you could do that. But emulators are really cool because they're built into antivirus software, which is known to have very poor code quality, known to be very vulnerable, known to be very complex and do a lot of things and have a lot of code rot. And at the same time, they provide browser-like primitives for exploitation. So as many of you know, in modern exploitation, you have to bypass things like DEP and ASLR, and you need things like info leaks. You need to dynamically build ROP chains. And you can't do that with a straight stack smash anymore. But an emulator provides you that Turing-complete environment where you can get an info leak, construct your ROP chain, choose to go forward with your exploit or not, tailor your exploit to the particular version of the emulator you're running in. And so that's a really interesting target to work against. They're very difficult to get at for all the reasons I listed before. They're hard to reverse engineer and everything. But if you have that knowledge and if you take the time to get at them and unpack that soft, GUI center at this, after this very armored shell around them, you can get at that, and you can maybe find some vulnerabilities in there. Like I showed the Binary Ninja stuff earlier. It'd be really cool to work on that. And also, they're a great target because if you exploit them, you get 1, initial code execution. 2, you get a privesc because they often run as system. So you're now running at a high privilege. And 3, you're running in the AV itself. So Normally you could go to get the system, but you could still get caught doing something suspicious by an antivirus product running from the kernel. If you're literally the antivirus product itself, they won't ever catch themselves doing something malicious. So it's a really great target. And Tavis demonstrated one vulnerability in ESET 2 years ago and hasn't done anything since. I've not seen any other work on AV emulators since. I was just at Infiltrate, and I got to talk to Tavis actually about his work and talking about his strategies and approaches and all the challenges of getting to that, being able to debug the thing. It's very challenging. So it's a really interesting thing to work on. I hope more people will. I guess I'm kind of towards the end of my time. I did have a quick literature survey on academic work in this field and kind of the fundamentals of emulation, why we never see perfectly accurate emulators. I'm going to skip over that for now and take questions, but if anyone's interested, I can share these slides after, and you can get a big literature survey. This is based off an IEEE paper I just wrote, where we cited 183 papers over the past 15 years on this topic and got a huge closure on all these academic papers on offense, defense, detecting malware, evading, mitigating, so forth, and some of the fundamental problems where, it's one thing to be in the AV industry and be working in the front lines of that million plus new pieces of malware every day, and something to look at the fundamental challenges of emulation. So skip right ahead to thank you and questions. Thank you to Jailbreak, Ryan Spears for inviting me and hooking me up with TMAC, my team that worked with me at RPI, and people who give me help and inspiration. I just have a demo as I take questions. We're going to dump at the Kaspersky file system in real time. Any questions? Thank you. Yep.
So that was great.
Thank you.
So I think what I heard thematically was, hey, emulators are really, really hard to do, and they're also really pretty easy to obtain.
Yes.
So if you take that, and now you're trying to flip around from a defensive perspective, what are your thoughts on whether or not it's even worth the effort?
I think what the AV industry and people who want to work on these technologies in general need to do is take advantage of the fact that evasive malware behaviors are likely discernibly different than normal program behaviors. The very fact that I ran the fold pi instruction is so strange. If I was running mathematical software, maybe I'd run that, or graphics modeling. In some cases, you do want to work with the number pi, but what software does the average consumer download off the internet, and in the first, say, 100 bytes, 100 instructions that it runs a fold pi? That's so strange and so aberrant, you could use that as a signal to detect that you're looking at malware. And what I'm showing is that there's really not evidence of that. That was one of the themes I touched on. Generally, they just kind of emulate stuff as accurately as they can, and really, really things that are clear red flags, like downloading a file from the internet that's a DLL and loading it to memory. That'll get you caught. Or scanning through all the bytes of a DLL to look for hooks. That might get you caught. But there are so many obvious behaviors that are so strange and bizarre and erratic that are just, they say, okay, I'll run fold pi for you. Okay, I'll run this API you called. I'll let you scan the PEB and walk the PEB loader data structure, which only really shellcode might do, or some like Microsoft internal function might do. Legitimate code doesn't do these things. So look for those signals and look for those as heuristics. Yep.
Have you by chance looked at those defender? Can you compare that to
I actually haven't. I've been meaning to.
any insider knowledge?
I haven't. I'd like to. Yeah, I've not looked at it. I've heard it's quite good. Kaspersky was the best one that I looked at. I think Microsoft Defender might actually maybe be better because it's built by Microsoft engineers. But again, that is still an emulator. It's not really the Windows API. We can talk more offline. I've heard some things from people, but I think Kaspersky was the best that I looked at, and I would like to look at Defender sometime. Any other questions? Yep.
Have you seen malware change as more legitimate targets become virtual systems?
So yeah, that's a really interesting line of research. I've worked more on this offensive side of things. I was there trying to bust these AVs. My knowledge of real-world malware behaviors in terms of evading stuff in the wild is limited to some of the stuff that I actually looked at that I found myself, or some of the APT that I was looking at that actually used the same techniques. My understanding from being in the industry and reading papers and everything is that there has been a shift towards more of these heuristic techniques. So there's a paper coming out at IEEE this summer called, I think it's Spotless Sandboxes. It's from a team at Stony Brook, and they actually cited this research in their paper. And they were looking at these kind of reverse Turing tests, things like the certificate revocation list that you're going to have, or there might be metadata. When I open a folder, it might cache the contents of the folder or something like that. There's just things that just cruft that accumulates as you use a system. Web history, photos on a mobile system, and they're looking. Are those artifacts present, or is this like a totally clean, fresh system? Has this system been running for 3 years but have no web history, no registry entries that related to when it was last turned on, turned off, things like that? So there's a move, I think, to using those sorts of very subtle techniques. There was a write-up. If you read the paper, they talk about some malware in the wild, some APTs that were using these techniques in the wild, rather than these traditional, is VBox sys there present. They were actually looking for more subtle artifacts of real user interaction, real user presence, and real history of a user on the system. So, yep.
Since you published this research, have you actually been aware of any AV products trying to improve their engines? Or?
Not that I've been aware of. I haven't really followed up since I gave a shortened version of this talk at Black Hat. This is a little updated, some new stuff. I was not aware of any AV products that have improved since, and actually Bitdefender in particular, I have looked at some, and I think those artifacts like test app is still in there. So I don't know. I mean, yeah, I don't know. The thing is, this is an annoyance to them, but again, real-world malware is probably already doing it. I think some of those artifacts I showed, those are strings. One way to get at those that's really easy that I didn't mention before is you run the AV process, you just run it, and then you just kill it, and you take a crash dump, and you just grep through your crash dump, and you'll find things like C testapp.exe, and you could very simply test, oh, is this, my name test app, or is my username this? You won't find CPU red pills and timing skews and all these very subtle inconsistencies that I was looking for with a technique like that, but you will find simple strings that you can just grep for. After they've been unpacked and loaded into memory, they're going to be there, and you can look for them in crash dump. So again, they were already fighting malware using those artifacts. The CPU red pills and stuff, you have to wonder at some level, do malware authors need those advanced attacks? And can they even implement them in some cases? I mean, like doing inline assembly with these bizarre instructions and touching floating point and stuff like that. Like a lot of malware authors, I wouldn't always have faith in them to actually be able to write code like that. So I don't know. I don't work literally in the AV industry, but I'm not aware of any improvements because of this work. Anything else? Any other questions? I'll be around after if you have any questions, and I'd love to talk. And also, if you do want to learn more about some of the academic side of this work, I'd love to talk about that as well. Thanks.